Alright, welcome boys and girls, ladies and gents, creatures real and make-believe. We're going to talk about stoichiometry. So it's pronounced stoichiometry. There are no storks involved in this whatsoever, even though there's one on this screen. So please don't pronounce it with any storks in the name. It's stoichiometry. Big fancy word you don't know much about yet, but you will by the end of this. It's officially defined as like the calculation of quantities in chemical reactions. It's how we get from one thing in a chemical reaction to another, be it in moles, grams, liters, or any unit. Stoichiometry will help us get from one thing to another. Before we do that, though, we have to know about conservation of mass. This basically means that mass, and therefore atoms, are conserved in every single chemical reaction. You cannot lose or gain any, no matter what happens. So in this equation, we've got aluminum plus oxygen goes to aluminum oxide. But note, that's why we had to add these balancing numbers in our previous lesson, because we can't have any aluminum disappearing or extra aluminum showing up. We have 4 aluminums on the reactant side, and we have 4 aluminums, 2 times 2 aluminums on the product side. Same thing with our oxygens. There's 2 times 3, 6 oxygens over here, and 3 times 2, 6 oxygen on the reactant side. That means they're balanced, they're the same, they're conserving the number there are, meaning its conservation of mass is shown, and they'll be the same way in every single reaction you ever look at. Alright, our big first concept is called the mole ratio. So ratio is just something over something, something divided by something. So it's a conversion factor that converts from moles of one thing, could be a reactant or a product, that takes us to another reactant or product. So in this equation we've got 3 things. We've got hydrogen, oxygen, and water. Now in our balanced equation we need 2 moles of hydrogen plus 1 mole of oxygen to make 2 moles of water. So we want to do a mole ratio. We have to ask between 2 things. In this case we're looking at a mole ratio of water to oxygen. So we need 2 moles of water here for every 1 mole of oxygen. So it's going to be 2 moles of water over 1 mole of oxygen. Okay, see? 2 to 1. So it's 2 to 1. Make sure you put the moles of water and the moles of oxygen in there. So we add more steps, it's going to get much more complicated. I can guarantee you'll be lost, and I won't be able to help you if you show me your work without those pieces in there. It's extremely important. Right, so our next one, as cute as these little moles are, we're not talking about those kind of moles, but the measuring moles, a mole meaning 6.02 times 10 to the 23rd of something. So 6.02 times 23rd moles of oxygen, 6.02 times 10 to the 23rd atoms of O2 is required to make 2 times that many atoms of water, not the furry little creatures. You can read it, pause if you need to. Okay, mole ratio example number 1. What would be the mole ratio of silicon nitrite to iron 3 nitrite be? Think you got it? Pause and try it. If not, I'm going to go through it now. Okay, we've got 3 moles of silicon nitrite because there's 3 as our coefficient in front of silicon nitrite, to a ratio of 4 moles of iron 3 nitrate because there's a 4 as our coefficient in front of iron 3 nitrate. So it's a 3 to 4 ratio, 3 moles of silicon nitrate over 4 moles of iron 3 nitrate. Cool. Let's try number 2. What would be the mole ratio of tungsten 5 chloride to tin 2 nitrite? Same idea. If you got it, pause and check it. We've got tungsten 5 chloride is right here. That's got a 2 for a coefficient. Since I asked that one first, it'd be a 2 moles of that over tin nitrite. It's going to be right here. So tin 2 nitrite to 5. So it's going to be 2 moles of tungsten 5 chloride over 5 moles of tin nitrite. Not too bad, huh? Okay, number 3. See if you can do this. If there's someone with you, pause it, do it by yourself, and check with them. Then check here and see if you guys agree with the answer. You've got 4 color choices this time. Hopefully your answer came out to be one of those four. Checking KBr to ALBr 3 mole ratio. KBr's got a 6. ALBr 3's got a 2. Like, oh, 6 over 2. If I divide that, that's 3 to 1. Careful, it should not be 3 to 1. You need to keep the actual numbers that are the coefficients in the equation. So make sure you use actual 6 to 2. It gets you red. If you put 3 to 1, that would be incorrect. So you actually need 6 to get 2 of those, because there's 1 here. You can't reduce the numbers any more than that. So you got to keep it the way it is. Okay, example number 2 here will be the mole ratio of lead 4 chloride to lead 4 nitride. Color choices again. Take a look, solve it, pause it, solve it, then check. Hopefully you got blue. 3 moles of lead 4 chloride to every 1 mole of lead 4 nitride. If you don't have questions, ask. Alright, let's look at cakes for our real life example. So I'm asking you how many cups of sugar you need to make 14 cakes. You could figure it out if you have the following ratio or equation or recipe. So I know this is a simplified form and not quite accurate, but go with it. This is our equation to make a cake. 2 cups of flour plus 3 cups of sugar plus 1 cup of oil plus 1 egg equals a cake. So they're asking for 14 cakes. We need 14 of these, which means our equation needs to become 14 times bigger. So we can make 14 cakes. Using our dimensional analysis, cakes have to cancel. So our cakes will go down here. And we're turning them into what the question wants? How many cups of sugar? So cups of sugar will go on top. So for every 1 cake, right here, we need 3 cups of sugar. So 1 cake, 3 cups of sugar. Cakes will cancel. We're left with 42 cups of sugar. That's a lot, but you're also making 14 cakes, so that's cool. This one should seem probably fairly simple. That's okay. And it's real life, so it seems to make more sense to you. When we get to the chemistry, if you use the same method, though, it'll work out every single time. Anytime a conversion problem works with dimensional analysis. Alright, let's do the balanced equations. Here's our same equation to make a cake. If we're saying how many cups of flour would you need to make 4 cakes, try and set it up with dimensional analysis and see which of the following answers you get. Pause. Check. Alright, you're back. Awesome. You should have gotten pink. Cancel the 1 cake with your 4 cakes, and you end up having 2 cups of flour for each, so you get 8 cups of flour total. Good. Now let's do the chemistry equation. If we're asking about, using the same logic, how many moles of magnesium would you need to make 10 moles of magnesium oxide? So start with what you're given, which is the 10 moles of magnesium. Cancel that. So moles of magnesium moles of magnesium oxide should be on the bottom, MgO. Moles of Mg should be on top. Make sure to use your coefficients from the equation. Hey, they're the same, so the math is really easy. 10 divided by 2 times 2 gets you 10. Alright, let's make it a little bit trickier. Let's change magnesium out for O2. So now we're still starting with 10 moles of MgO, but now we're going to moles of O2. So when you cancel them this time, moles of MgO will still be on the bottom, but moles of O2 should be on top. When you do that, your math comes out to 5 moles of O2 being left over and not canceling out. Hope this is making sense by now. Because now we can step it up soon. Alright, so one last one I think. If we ask someone the number of moles of lithium that are required to make 12 moles of lithium oxide, you can use the following ratio. 12 moles of lithium oxide is what you're given. You always start with what you're given. We're going to need to cancel moles of lithium oxide down here and go to moles of lithium on top. Those numbers will come with their coefficients for their ratio. Right? 2 moles of lithium oxide because there's a 2 in front of lithium oxide in the balanced equation. 4 moles of lithium because 4 is the coefficient of lithium. gets us a total of 24 moles of lithium needed to make 12 moles of lithium oxide. That's your mole ratio steps. If you want a general mole ratio formula, it's the one in red at the bottom. Note how moles of A cancel moles of A. You'll have to moles of B, get you moles of B. Whatever moles of B can be anything else in the equation. Go from reactants to products, products to reactants, product to product, doesn't matter. Any two things in the equation, if it's balanced, can get you from one to the other. Okay, so if you want, it makes it easier, you can think about having this whole thing, the moles given, over 1. You don't have to, it'll still work either way. Just general dimensional analysis, canceling, converting thoughts. Make sure the bottom unit here always has the same unit as the one up here. If that always is the case, and these two are even, it'll always work out. Alright, let's step it up. Let's do moles into mass. Two-step problems. You got this. So let's say you got 6 moles of magnesium and excess nitrogen. For now, we don't have to worry about the nitrogen because it's excess. We got lots of it, so it's not going to come into play in our equation. How many grams of magnesium nitride would you have? Now, we already know how to convert from moles of one substance to moles of another. That's what we've been doing for the last few minutes. But saying you have 3 moles of sulfur doesn't tell you much. Oh, I've got 40 moles of sulfur. Wow, you must be really rich. I know absolutely nothing about what that means. Is that a little? Is that a lot? We only talk in mass. It's the only thing that people know. Well, you guys aren't familiar with grams. Scientists are. When we talk about pounds, you know what those were. So now we need to know both about the mole ratio and the molar mass of that compound. So we need the equation. So here's our equation between magnesium, nitrogen, and magnesium nitride. Cool. Then we need to convert from what we're given, which is the 6 moles of magnesium. Now we're not going to use the excess nitrogen because it's extra. It won't run out. We only need to worry about the thing that is going to run out, which is our magnesium. We need to cancel moles of magnesium down here and go to the moles of the thing they're asking for. So they actually want grams of magnesium nitride, but you can't do that if you're changing both parts. You only change one thing. So we're going to go into moles first of magnesium nitride. You see they're both moles, so that's fine. Since these are both moles, we can change the of what. That part can change. Now that we're in moles of magnesium nitride, we can go and cancel moles and turn into grams of magnesium nitride. Now this grams per mole, molar mass, this number I got by adding up the mass of 3 magnesiums off the periodic table and 2 nitrogens. When I total them up, I get 100.9 grams. Now everything on the bottom is canceled. The only thing we're left with is grams of magnesium nitride, which is, hey, what they want. Now we have to do the math. 6 divided by 2 times 1 if you want, but it won't do anything. Divided by 1 if you want, but it won't do anything. Times 100.9 will get us an answer of, oh, I'm hiding it, answer of 201.8 grams of magnesium nitride. Easy peasy, hopefully. Make sure you have the example down so you can reference it back if that wasn't easy for you. Oh, that's just chilling out there. Well, we'll get to it. Alright, let's look at an example of Shauna the swimmer. She loves swimming so much. She decides to eat 800 grams of glucose. So how many moles of CO2 would be produced? If you think you got this, pause, then come back. Go through this one a little bit faster. Right, so we're given 800 grams of glucose. So we're going to start with that. It's an equation we use a lot in biology next year. We're going to cancel grams of glucose and go into moles of glucose. Because we can only go from one thing to another when they're in moles. So now that we're in, this is the molar mass of C6H12O6. Once we're in moles of glucose, that's great. We need to get to moles of CO2 that popped up early. So we need to cancel moles of C6H12O6, glucose, and go into moles of CO2. Now it's mole ratio, moles on top, moles on bottom. This is the long version or the short version. These numbers just come from the balanced equation. That's what we want in the end, so we solve it, and we get our answer of 26.65 moles of CO2, and those are your two-step problems.